So we came up to this expression of the sampled version of the signal in frequency domain as given in this expression number 3, or probably we can call it this thing as 1 because we're starting this lecture. So as 1, and then we expanded this for various values of n, and for n is equal to 0, n is equal to 0, equation 1 results into this first term. Similarly, n is equal to plus minus 1 results into this second term, and similarly, n is equals to plus minus 2, it results into this term, and so on and so forth. So it will go ahead, but we have not written these terms. So we said that let xct in time domain given by this expression, given by this waveform like this, has a Fourier transform of this. Okay. So this was an assumption that the Fourier transform of a signal looks like xct, xcj omega. So where whatever is the frequency or spectral representation of the signal, we can assume, we can take that and then proceed further. Okay. So now st in here was a impulse train, which was given by the expression 1 upon t, no, summation del t minus nt, where capital T, this was the sampling duration. Capital T was the sampling duration. Yes, and similarly, we knew that if we want to obtain the equivalent frequency domain representation of this, of the impulse train, we knew that this in frequency domain is another impulse train with period omega s, with period omega s. Now what we wanted was, we wanted to have this sampled signal. We wanted to have this sampled signal in frequency domain. So if I wanted to obtain this, if we wanted to obtain this sample signal in frequency domain like this, so it turned out that if the signal is band limited to 2b hertz, that is minus v to b hertz, then in that case, and if that is less than 1 upon 2t, or less than omega s by 2, in that case, the signal came out to be like this. The signal came out to be like this, okay. And for we constructed this again using this expression 2, and for n is equal to 0, for n equal to 0, this is corresponding to exactly omega c, sorry, xc or j omega. So this was this plot, this part of the figure. And similarly, if we consider this at n is equal to plus minus 1, then in that case, these were corresponding to these two impulses. These were corresponding to these two impulses, convolution with them, and these came out to be this portion and this portion. Yes, these came out to be like these in here. Okay, so then we expanded this thing further. Okay, let me just redraw this thing again. Let me redraw this. The reason being, or rather, instead of erasing, let it be there. Yeah, let it be there. Let me just redraw it afresh. Okay, so what I want to do, I want to zoom this thing in so that we can have a better angle at it. Yeah. So if I see this, if I see only this portion, or probably okay, or let us take the axis only in frequency domain, that is in hertz. frequency domain. Yeah, and then draw this thing after expanding it a little bit. Yes, and like this, and then this is going to continue in here like this. So, okay, okay. So, what are these values? This is 0. And what is this value? What is this value? Do people recollect this and this value? What are these values?
B minus B 1 by T minus 1 by T.
B minus B something else. Yeah, 1 by T, and this was 1 upon T. Is it? Was this 1 upon T? And
Yes,
this
I guess
this
so.
was 1 upon 2T. And B was this. B was the bandwidth of the signal, minus B and plus B. It was this. It was this. This was B. Okay. Where capital T is was what? Nothing but the sampling duration. Okay. Is the sampling duration. So now, having said that, if I see that if B is more than 1 upon 2T, in that case, what should be the resultant signal? If I sum these three parts, that means this, this, and this. If I sum this, what will I get? What will I get? It is linear in this portion. So this is linear in this portion. So for this portion, and again for this portion, I should get, I should get something like this. So this is what we are going to get, like this in here. So this will continue like this. So this will be what? Excess j omega. So this will be excess j omega. Uh, this is okay. This will be excess j omega, but this excess j omega, if I see and compare it with the transmitted, that means xc j omega, the original the original message signal, that is xc g omega and excess g omega, are they similar? Are these similar? Are excess g omega, okay, I should not say excess g omega, I should say excess g omega when passed by a low pass filter. If I pass this thing by a low pass filter, okay, so if I pass this thing by a low pass filter, by an LPF, so whatever we get is, this is not equal to xcg omega. So if I pass this thing by a low pass filter and let the filter be, so we knew that the filter in the best case can be like this, to make it more and more close to xcg omega. Okay, so and let this be the LPF. this be the LPF, and if I pass this thing by an LPF, even then what we will get is not same as xc omega. Is this point clear to everyone? This one, is this clear to everyone? Anyone who has got doubt in this, that if you pass excess j omega over a low pass filter with a cutoff frequency of 1 upon 2t, okay, LPF.
Sir, all this is the case if B is greater than 1 by 2t, right?
Yes, yes. If
If
f
B is
is,
less than 1 by 2t, then if we pass low pass filter, then we'll get Xc of j omega.
yes, yes, correct, correct. Yeah, who was this?
So Srishti.
Shrishti, yeah, Shrishti. Shrishti is correct on that. So this, okay, okay, what Shrishti is saying, let us write that also. So if we say it like this, so what we can say, we can conclude it like this. This is equals to xc j omega for the case, when, and this will not be equal to xc j omega. When, what is the condition on the bandwidth?
B is less than 2t.
B is okay. Okay, let's derive this condition also. So what do we want? We want that this is B. This is B. We want, what do we want? We want this 1 minus TS. So we want this part. We want, so what is these two parts? What are these 2 points? Let us say. Let this be. So what is this point? This point is defined as 1 by Ts minus B, 1 by T minus B, sorry. Let's derive this also, 1 by T minus B. Yeah, this point is 1 by T minus B. And what is this point? This point is B. Okay, this point is B. So what do we exactly want? We want that this 1 by T minus B, we want that this 1 by T minus B, this should be greater than B. Is it or not? We want 1 by T minus B should be greater than B, and this is the condition for this distortion, no distortion. Okay, by the way, I haven't named this distortion. This distortion is called as aliasing. This this portion is called as aliasing. This is nothing but aliasing. Okay, this is called as aliasing. And let's come back to the case when we want there is no aliasing. So we want that 1 minus T, 1 by T minus B should be more than B. So this is the condition for no aliasing. So if I solve this thing further, what am I going to get? So I can say if I solve this thing further, this is 1 by T greater than 2B. Okay, or 1 by T greater than 2B. And what is 1 upon T? 1 upon T, what is that? 1 upon T is the
Frequency.
frequency of what? T was the sampling interval. So 1 upon T should be?
Of impulse train.
No, so if you see in here, if I see this, T was the duration of the impulse train. So that eventually says that T was the duration for, this is the sampling duration. T is sampling duration. So 1 upon T should be what?
Sampling frequency.
It is sampling frequency. So I will write this thing sampling frequency as Fs. Okay, Fs should be greater than 2B. Okay, Fs should be greater than 2B. I am not writing equal to. There is a specific reason behind it. So Fs should be greater than 2B. So this is what we obtained the sampling theorem. This is the sampling theorem. This is the sampling theorem, and I'm specifically saying fs greater than equal to b. I am not saying greater than equal to b. I am very particular about saying, not saying this thing that this is equal, greater than equal to. It is strictly greater than 2b. Okay, it is strictly greater than 2b. So it is not greater than equal to. So I just wanted to highlight this. Yeah. The other part is, we knew that. So what is the Nyquist rate or interval? So again, the Nyquist rate or interval is nothing but fs is equals to 2b. At fs is equals to 2b, or t is equals to 1 upon 2b is the, this we have already studied. I am not going to go over it again. Nyquist rate or interval. Nyquist rate or the Nyquist interval. Yeah. So these are the important, some of the conclusions. So, and now we can come back in here because we have already seen this. So this is equal to this thing for when, what should I write in here? When fs should be greater than 2b, is it or not? And this when otherwise. This is not equal to xc. This is what we have deduced. So is these points clear to everyone, what we have just now done? Anyone who has got any doubt in here? Yes. Yeah. Are these points clear to everyone?
Yes,
Yes
sir.
or no? Yes. So at the Nyquist rate, what will happen? Let us draw once more this figure, and let us see what will happen exactly at the Nyquist rate. At the Nyquist rate. Okay. At the Nyquist rate, what will happen? At fs is equals to 2b, what will happen? At the Nyquist rate, what will happen? We will have exactly these two. Okay. At Nyquist rate. At Nyquist rate, the figure should be, the above figure is going to look like this. And the low pass filter, equivalent low pass filter, would be exactly the limiting case. Okay. So I will now use again the same color to indicate what was. Okay, let me just change the color to green. So this color green, this is nothing but xc, no, xs sampled, xs j omega, and this is in red, this is LPF, low pass filter, and if we pass this thing by low pass filter, we get the desired signal, which is going to be xst. Okay, so this is the case at the Nyquist rate, so at the limiting case. But sampling, for sampling theorem, I am not willing to say this thing as greater than 2b or equal to 2b, greater than equal to 2b. I am not including this equality. The reason being that if we consider a sinusoid signal or a cosine signal, what should be the Fourier transform of the sinusoid or cosine signal? So if I want to consider the Fourier transform of a sinusoid signal or a cosine signal, then there will be a trouble. Why? Because the impulses will be exactly overlapping at this interval minus 1 upon 2t. Yes or no? So if I had a signal, sinusoid signal input as let xc. Okay, let's not go into this at this stage. I guess this is something that you have to wander around. What happens? Let me write. Okay, not what happened. What if xct is sine sine, let us say, what do I say, omega s, the sampling duration omega. So no, not this omega, or yeah, sine omega s. Yeah, now this is sine omega s, and omega s is nothing but the sampling frequency. Okay, omega s, how have we defined this omega s? Yes, omega s is this value. Yeah. So should I be saying omega s? So it should be omega s by 2, because this is periodic with omega s. So it should be, yeah, omega s. Okay, so if this is the case, then if what if x is equal to this, can we reconstruct? Can we reconstruct? So what have we done in here? So this is another question that you have to pause and ponder. Okay, this is question. This is a question where you have to pause and ponder, and you have to think over this thing, because this will lead to whether fs should be greater than, equal to, or greater than 2b. This is going to lead to this, not fc, yeah, fs, sampling frequency, greater than or greater than equal to 2b. Yeah, so this is something that you have to pause and ponder. Now if I see the reconstruction part in the frequency domain, we have already done the reconstruction part while figuring out if we want to eliminate aliasing. If we eliminate aliasing, irrespective of that, this portion itself, if you pass excess j omega with low pass filter, this is what? This is nothing but reconstruction. This is reconstruction. So whatever we receive, if you pass it by a low pass filter, okay, where mod f is less than 1 upon 2t, in that case, whatever we get should be fc, should be xcj omega, provided we have followed this sampling theorem. If the sampling frequency fs is greater than 2b, if fs is greater than 2b, then whatever we are going to get will be xcj omega if you pass it by a low pass filter. Is this thing clear to everyone? How did we actually did reconstruction? So in this, if this was xcg omega, okay, let us draw beneath it again so that it is more clear. Okay. Yes, so now if I have, instead of writing the low pass filter in here, let's draw the low pass filter again. Let this be the low pass filter, this be LPF with plus 1 upon 2t and minus 1 upon 2t. So if I pass xs j omega with LPF, what should I get? I should get this. And which is what? Which is exactly same as, this is what? xc j omega. Okay, xc j omega or if we take the inverse Fourier transform of this is xc t. Okay, this is xc t. If we take the inverse Fourier transform of this, we get xc t. Okay, so now this is what it happens. But what do we understand by this thing in the time domain? Because we are not going to do this operation in the frequency domain. So we have to try to understand this in terms of what? In terms of what happens exactly in the time domain, because this is the time domain signal is the signal that we want to process this thing. And other thing that we wanted to obtain is that how do we equivalently write this low pass filter? How do we represent this low pass filter in the equivalent time domain representation? So this is what? This is LPF where h j omega or whatever h omega is equal to 1 for mod f less than 1 upon 2t, less than 1 upon 2t. Yeah. So if this is the case, so let us now start seeing reconstruction again. Now we want to see this thing, understand this in terms of the time domain signal. So we knew that HF, let this HF be nothing but this LPF response. So then in that case, we knew that XCF is obtained via passing XF, XSF by this frequency response HF. If you pass this thing by HF, we get XCF. Is this expression clear to everyone? Anyone who has not understood this expression? This expression in here. Anyone who has not understood this?
Sir, are you multiplying both of them?
Yes. This is how we get it. If I am writing this transfer function, if I see this block diagram, if I see this block diagram, this complete block diagram, so how do we get the resultant XCF or j omega, whatever? Yeah, that will be the multiplication of this. Yes or no?
So, sir, it will happen in the frequency domain. So, in the time domain, it will be a convolution operation, right?
Yes, correct. But I'm asking about equation number 3. Is everyone following this? Equation number 3 is correct or not? If you are convinced on that part, then we will go ahead in the time domain. Is everyone convinced for equation number 3 that is this thing correct?
Yes, sir.
Yeah. So what we want to deduce is that we have seen this thing in pictorially, that if we pass it via low pass filter, then we can get the original signal XCT. Now what we want to do is we want to formulate its mathematical equivalent, that what should we be doing mathematically so that we can reconstruct the signal. Okay, this is what we wanted to have. So that's why from the figure we knew in frequency domain, if we pass it by a low pass filter, we get XC j omega. So that effectively means equation number 3. That equivalently means equation number 3. That equivalently means equation number 3. Now, if I want to go back, what can I do in the time domain given equation number 3? So then in that case, we knew that we have to convolve XST with HF, where HF is nothing but the inverse Fourier transform of capital HF. So before I go ahead, we have to revisit what is the inverse Fourier transform of this function. I'm going to ask you all this again. What is the inverse Fourier transform of this rectangular function? What is that? Do people recollect? If I say that this is TS, okay, and this is minus B and B, this is again in frequency F, in F, and then in that case, and I represent this thing as a rectangular function, which is HF in frequency domain is given as TS
It will be a sinc function.
It will be a sinc function. Yes, correct. F upon 2b. F upon 2b. If I want to take the inverse Fourier transform of this, okay, this is ICTFT, inverse continuous time Fourier transform. Yeah. So this is not in F. This becomes in time domain T. And how does this signal looks like? This signal is like this. This signal goes like this. Like this. And these zero crossings are happening. These zero crossings are happening. These zero crossings are happening at 1 upon 2b, 1 upon b, and so on and so forth. And this is 0. And the amplitude is, maximum amplitude is 2bts. And this is what? This is nothing but ht. So this was hf and this was ht. So if I have to write this ht mathematically, this ht is given as 2bts times sinc function 2 pi b t. Okay, sinc function is this, where we see that at if I see at t is equals to plus minus 1 upon 2b or n times time n, this at t is equal to this where n belongs to an integer, this value, then in that case ht is what? Ht is equals to 0. Then in that case ht is 0. Ht equal to 0 or rather I should say it like this. Yeah, fine. Ht is equal to 0. So is this part clear to everyone, what we have just now said? So HF in frequency domain is given by this expression in here, and the equivalent time domain representation of HF is again is just going to be sinc function, where we knew that ht is equal to 0 at time t is equal to plus minus 1 upon 2t. So we know this thing from equation number 3. From equation number 3, we knew. And one more thing, if I see this at t is equals to plus minus 1 upon 2b or n upon 2b, so at these points, but what we know? We know this thing also. If t is equals to what? We knew this Nyquist rate also, which was, what was the Nyquist rate? Nyquist rate was 2b ts. 2b ts was equals to 1 at Nyquist sampling rate. So this will come into picture, just hang on with that. Hang on with this. So HT, we knew that this is, so if we assume this thing is happening at the Nyquist sampling rate, so, or probably I should be writing this one here. Yeah. At Nyquist sampling rate, this is at Nyquist sampling rate. Two BTS is equal to 1, and we have HT given as 2BTS, saying 2 pi b times t. So if I put 2BTS is equal to 1, as we are doing at the Nyquist rate, so this becomes what? HT is nothing but 2 pi b t. Okay, and if I see equation number 3, from 3 we knew from 3, we have what? XC, probably I should write it again, below XC. I'm going to write this thing in F as HF times XS F. And now if I want to write the equivalent in time domain, so this becomes XC T is equals to HT convolved with what? XST. So what have we concluded in here? We have concluded if we do the convolution of the received signal with this low pass filter HT, where HT is given by a sinc function, then what we will get? We will get the original signal. We will get the original signal. Is this part clear to everyone? Anyone having any doubts in here?
So I
Anyone?
have a doubt.
Yes, go
I
ahead.
actually did not understand the line that you wrote below the Nyquist sampling rate. So the second line, h of t equals 2b as sinc function I've written, and the next line I've written h of t equals sinc function to be
Because
2
we
pi
are
dt.
because if this is Nyquist sampling rate, then we know that 2b/Ts is equal to 1.
So actually the thing is, I don't know, but I feel
Mhm.
we haven't gone through the Nyquist sampling rate already in the, I mean, SNS. So if you could give a
So
little
this
idea
is,
even about
yeah,
it.
this is it. This is it. We have already written it here. You know, the Nyquist sampling rate is the critical rate. You cannot go below that. You cannot do below that. This is the minimum rate. It has to be so. If the sampling theorem is like this, that Fs should be greater than 2b. So the Nyquist rate or the Nyquist sampling rate is the critical rate. So you cannot go beyond that. I mean, you cannot go below that. You can go always ahead of that. So that means in that case, T 2bTs is equals to 1 is the Nyquist rate. In a very, it is a very short version of Nyquist rate. Yeah. So this is the condition. I hope this is clear.
Okay, sir.
Yeah.
Okay, so yes, sir.
So then in that case, we get 2bTs is equal to 1 as the Nyquist sampling rate, because we are doing the sampling at the Nyquist rate. So then 2bTs is equal to 1. If we were doing this thing higher than that, then this 2bTs would be equal to 1 or 1.5 or 2 or whatever. Okay. So this is just the rate at which we are doing the sampling. So in that case, there will be a constant in here, nothing more than that. So that will not affect anything. So then in that case, we get equation number 4. Are people able to follow this part? How do we get equation number 4? Everyone convinced on equation number 4?
Yes, sir.
Everyone convinced on equation number 4. Okay, that's good to know, but yeah. Okay. So now if I want to draw this thing, if I want to understand this thing again pictorially, we have already seen this thing in the frequency domain that it looks like this. In frequency domain, XS j omega looks like this. And LPF, if you pass this thing with LPF, low pass filter, then it will come out to be like this. But what exactly is happening in the time domain? What exactly is happening in the time domain? If I go back to this signal, how are we going to get on earth from this signal to back to this signal? We had an impulse train, uh, the amplitude of the impulse train was originally decided by the XCT, the message signal. But how on earth we are going to get this from the impulse train with amplitude of XCT back to XCT? How are you going to get that from this operation? It's still not clear. So if I want to now again draw this, so what is going to happen? If I just see this, if I just see the convolution between the two of them, so what will happen to HT? HT, if I now again write this thing, XCT, if I write this XCT is equals to, in terms of this convolution, so can I write this thing like, because so this, we are considering the kth sample, so this is again being sampled, so I'm going to write this thing in summation, okay, in the form of the summation, and then can I write this thing as XS KTS times H of T minus KTS. Can I write it like this? Summation over K varying from minus infinity to plus infinity. Output of the filter. Why? Because this 4, because we know XST is what? The sampled version. So it will have impulses only at t is equal to NTS. T is equal to NTS. So I can equivalently write this thing is in equation number 5. I hope this equation number 5 is clear to everyone. Anyone who has not understood equation number 5. If that is the case, if this is clear to everyone, then I can write this thing as what? I can write this thing as KTS times the sink. KTS. Okay.
So
Yes.
I T equal to NTS.
T is equal to, if I see this sample signal of ST, okay, if I see this ST, sample signal ST, so it will be what? It will have non-zero values only at T is equal to TS and TS, where TS is equal to T. So NT. It will have non-zero value only at T is equal to NT. Otherwise, it will have zero values.
So T equal to TS. Okay.
Yeah. So TS is equal to T. TS and T are same. Capital T and capital TS, they both are same. Do not get confused in here. So in this entire lecture, capital T and TS is same. Okay, capital T and TS are same. Not the small t, but capital T and TS are same. Okay, so if that is the case, can we write this? If we can write this, then what is happening in here? Now let us see this thing. Let us see this thing. At the kth sample of the input, XST. So kth sample of the input, this is XST, is what? Is the impulse. What is the impulse? This is XC KTS times del of T minus KTS. Is it or not? So this is again going into the mathematics. This is again fairly simple. Let it be like here down only. Yeah, so XST is nothing but XC times del of T minus KT. So in that sense, what we can do, we can replace this thing XST by XCKT. We can replace this by XCKT. We can replace XS by XCKTS, which I said earlier, because this is an impulse sitting at NTS, okay, an impulse sitting at NTS and rest other places, this is 0. So what do we get? We get this XCKTS, or rather I should be saying this thing ahead and then writing it. Yeah, that would be easier. Yes. Okay. Yes. So now if I want to draw this, if I want to again see this thing, we want to see this reconstruction. How does this thing looks like? So XCKTS, the value of the signal at XCKTS, okay, XCKTS, and then this is being convolved with sinc function. So effectively, how it is going to look like is that it will be the summation over, so this was the message signal. Let me zoom in and then draw this. So this is the message signal, and this is XCT. This be the message signal, and we knew that the impulses are sitting at NTS. The impulses are sitting at NTS. Let this be NTS. So what will be the sync 2 pi b t minus kts? So that at t is equal to 0, this will be sync sitting at that value. Okay, sitting at that value with an amplitude equal to the amplitude of the impulse function, because we have said that this 2bts is equals to 1. This is equals to 1. So then in that case, and again see the zero crossings. Zero crossings are again at 1 upon 2b, interval of 1 upon b, 1 upon 2b. So that again this, so if I now check this, this is, let this be n by 2b. So what should be the next one? It should be n plus 1 by 2b. So if I assume that this value, the center one value to be equal to 0, this is corresponding to equal to 0. So then there will be a sync function sitting at this, which is exactly going to start, which is going to have an amplitude of same as this, and it will cross at these points. Yeah, it will cross. So let me just highlight these points. Yeah, it will have a crossover at integral of these, like this. All of them like this. Now, what will happen at t is equal to ts? T is equal to ts, it will be shifted by ts, that is this duration. So the impulse will be sitting at this point, So not impulse, yeah, impulse sitting at this point. So then that is sync will be shifted by ts. This sync, so this is sync at 2 pi b t 2 pi b t. Let us write 2 pi b t b t. Now I'm going to draw another sync which is shifted by t minus ts. This is shifted by t minus ts, and then this is has to be multiplied by what? This is multiplied by xc kts or xcts in here, this value. XCTS, or again, if I even see this XSKTS, that is also going to be the same thing. It doesn't change anything. So it is going to have an amplitude. The sync function is going to have the maximum amplitude of this value, and again shifted by TS. If this is again shifted by TS, this will have crossovers again like this. So forth, so on and so forth. So if I again draw similarly for minus ts and other values, so we can see this. We can see this. So the another one, if I continue this, this would be like this. Okay, so is this thing making sense? So if I now see at integral multiples of ts, it has got only one value. Okay, it has got only one non-zero value. If I sum these plots, okay, let me just write this also. This is what? This is sync 2 pi b t minus 2ts. Okay, now if I sum these up, in here it is what? It is the summation. This is the summation over all these values. So if I sum this up at each value, at each of this crossover values, that is n upon 2b, at each of this n upon 2b, what do we see? There is only one non-zero component. If I see at this point, if I see at what color should I pick? There is no color left. Okay. If I pick, okay, rather than this, yeah. If I pick this point, if I want to see this, there is only one non-zero value, which is here. Similarly, if I pick this point, there is only one non-zero value, which is this point. Okay. So, and this is exactly what? This is the point given by xct only. So then if I sum these things up, so I will get this xct continuous of xct like this one. We will get this. Upon summing, we will get this xct. That's how this operates. That's how this operates in here. That's it from my side at this point. If you have any questions, you can go ahead and ask. Any questions?
Sir, actually, we have to take the convolution of XST and HT.
Yes.
So,
Yes. So we only do this expression only. At receiver, we do only this expression, but I have just now shown to you that this is same as this. So forget about this expression. This was something else to, so you can forget about this. What you are going to do at the receiver is you are going to convolve this with this, and we knew that XST can be given as like this at t is equal to at t is equal to ts. Yes or no?
so you're like, how can you assume previously? Like, I'm not able to understand. Like, how can you assume XSTs, XC, KTS into delta of
Don't
TS?
assume. If you see question number 5, if you see question number 5, okay, if you see equation number 5, and I have drawn equation number 5 only. In here, what we have done, we have drawn equation number 5 only. Nothing more than that. The additional thing which I have said is that at xs at t is equal to nts is same as writing in terms of xct. Can we do that or not? This is already
Yeah.
known to us. This is how we obtained this. This xs is what? Xs is nothing but st times xct. Yes or no?
Yes, sir.
Yes, this is what I have written. I have not written anything extra in here. I have written that only. I have written this only. So equation number 6 is just to show you the equivalence, that how does equation number 5 turns into, so how do, after doing equation number 5 in time domain, if you obtain the figure, why it is coming out to be xc. So equation number 6 is to show that. That's it.
Okay.
Yeah, I hope this is clear now. So actually we have done, we have in here drawn equation number 5 only. Okay, this is just to show you what is the relation between xs and xckts, because you would be wondering about this line, this dotted line in red. How am I doing this? So just to show you the equivalence, that's why I've given this expression, which we already knew at the transmitter itself by doing the sampling.
So, sir, in this, what you are
Mm-hmm.
trying to do is, so first we have excess KTS, and then you are
Mm-hmm.
replacing it with XC KTS delta into T minus KTS, and our transfer function is this async function, right? So, yeah, so
Yes,
that is what is the equation 6.
equation 6, yes, but we can do everything from equation number 5 itself. At the receiver we will have excess kts, yes or no, and we will have excess and we will have ht. We will just convolve them and we will get the output, and that output will be this figure in green, that plot in green.
Okay.
This is just to show you why this will be exactly figure in green. The plot in green. The equation number 6 is just to show you that why this will be same as xc. Why this is same as xc. Why equation number 5 will result into xc.
Okay, sir.
So
Okay.
in equation 6, you need to have delta into t minus kts also, right?
Yeah.
You're replacing excess t.
Yes. If you multiply that again, the samples are only taken at ts only. Yes or no?
Yeah, so that's why we need into delta of t minus kts, right?
Into so but that thing is taken care in sync function because sync again so you are saying xckts multiplied by
Into
no but I have written this thing na xckts we have written this xckts and it's summation over k. It is not integral now. This is no longer integral, this is summation now. So we are only
Also, sir, in the beginning, the functions are continuous. So why are you writing it as a in this sigma form and not in the integral form?
yes, if we were doing if the signal is in continuous domain, okay, so then that is fine. Then we have to write it in integral. But now if I see this thing that I am taking the samples at only at TS and these samples are only the samples that are being considered. So don't you think that this integral will automatically convert into an summation? And first part. Second part is that this is more workable.
okay, sir. So like you're saying xc of kts, like even if you don't write delta of t minus kts, it will be the same thing because it is an k is an integral value here.
Yes, because we are saying k is again what belongs to integer from minus infinity to plus infinity. Yes, it won't change anything. Yeah, I hope. Any further questions?
Yes, sir. So in this
Yes,
fifth
go ahead.
equation, so it will be an integral, and then once you put this delta into t minus kts, after that
Yes,
it
then
will
it becomes
become
a
this
summation.
sigma. Yes, sir.
Or
So like
no, so in fifth it will be summation only. Why? Because even for excess, this will be summation. Why? Because if you actually see excess is non-zero only at multiples of ts. If you see this excess is non-zero only at t is equal to nts.
okay. Yes. Yes, sir.
So even equation number 5 will be summation only. So
Yes,
what
sir.
we have
Yes, sir.
written equation number this above 5 convolution, that is equation number 4, that is integral.
Yes, sir. Yes.
Okay. Any further
Okay.
questions?
Thank you, sir.
Okay, most welcome. Then we can stop at this point here.